Okay, hi and welcome to Notes 8.8 Exponential Decay, Day 2, Part 2. And in this one, we're actually going to focus on what we call half-life. And half-life is something that we use actually all the time in science, or science specifically, but a lot of sciences, where it helps us find the age of different things. So it's actually fairly common. You'll hear about half-life, so we're going to explore that a little bit. Here's the great part about it. It's an exponential decay. So it's actually one of the easier ones that you're going to have to do because it decreases by the same amount each time. Its name is half-life, so in half or 50%. So you'll actually like that because that's going to be your B value. So now that we've talked about it a bit and you kind of get an idea of what we're going to do, let's jump down into it and get started. All right, so in this, let's start real quickly with a quick decay problem so that we can have a little review on that and we can talk about it one more time. So in this one, if you do, most of our decays will be, for at least this section, will be about population, human population in general. Most of the problems seem to be written around because we keep it pretty basic. So in this problem, let's go ahead and see if we can identify all the parts. Just a review. In 1990, the population of Washington, D.C. was about 604,000 people. Since the population has decreased about 1.8% per year, or since then, shall I say. So first, you should always start off by writing down your base formula. And we've got a few now, and we'll recap that at the end. But here we've got the decay formula. And remember, the difference between a decay and a growth is just one thing, and that's a subtraction sign. So what we're doing is we're taking 100% of the original and we're subtracting off the rate that it's decaying at, which sounds weird because it's decaying at 1.8%. So a lot of kids want to write 1 or 0.018 in here. That's wrong. You do not want to write that if you are writing this function. You wouldn't want to put in the parentheses here 1.8, or do what you actually should do, is 0.018. That's decaying by 90%, almost 90%. That's too much decay. It's going to be just a little bit less than 100%. So now that we've kind of got that talked about again, let's go ahead and see if we can fill in the parts that it's asking for here. And we'll do it on our own because we've got a pattern. We write down the base formula and then we identify all the parts. And we should write that on each and every homework that we do, especially in these sections here. So the first part then, A, our initial amount, the amount that we start with, you can see I've covered it up a little bit, is 604,000 people. So we're going to write 604,000 people. And we're just identifying this for ourselves, and then we'll go and answer the question. And you can see that that one actually matches. The rate that we're decaying at technically is 1.8%, but if we want to make it a decay factor, we first need to change that to a decimal, so 0.18. But remember, the rate that we're decaying at is, this is 1.8% less than 100%. So we need to subtract that from our actual decay rate. So in this case, we're going to find it's going to be 0.982. So that's going to be our decay rate. That's 1.8% less than 100%. So we're not growing. We're actually not growing as 100%. We're growing just a little less, and a little less, and a little less. And that's why it's a decay. Our B then is our growth, or B here for this our question is our growth factor. We don't have a B. I don't know why B is in there. We don't have a B for this particular formula. We have an A, we have an R, and an X, or a T I wrote there, so we'll change it to an X because X is usually time in this case. And our time frame for this would be, if we were doing it, doesn't give us that part yet, but if you see here, write the equation to model it since 1990, and then it's supposed to change in 2010. So if we cheat a little bit, we find out that it's going to be 20 years from 1990 to 2010. So theirs would be the pieces that we would identify if we were doing this problem, but it's broken up for us. So let's finish off, make sure that we've got all the parts answered. There is our 0.98% or 0.982%, our decay factor, right? That's our decay growth. And then here's the function if we were to write it in there, because it says write an equation to model the population since 1990. Actually, this is a little misaccurate. This should be this, and it should be f of x, because it doesn't ask us to evaluate it. It just says write the model. So that would actually be the model for that one. Your initial amount of people, your decay factor, and then x would be the amount of time that passes. And the last one says suppose that the current trend of population continues, predict the population in 2010. That's where we get the 20 from, because it's 20 years from 1990 to 2010, and then we would plug that in. So what would that look like if we were plugging in? That's what I had written there originally. So evaluate the function at 20 years is 604,000 people at 0.982 decay factor and 20 years. And if you put that in your calculator, you'll find out that the population decreased from 604,000 to 420,000 in 16.83. So you would say 420,000 and 17. We rounded up. Yeah, that's semantics there. So that's just a little review on decay so that you can kind of see it as it is. Now, half-life, you'll actually find it easier because the decay factor, you don't have to subtract anything from 100% because it's always the same decay. What we do with half-life is that there's these isotopes that break down over time. And there's different isotopes, and they break down, some are faster, some are slower. But the way that we measure them is always by how much they decrease by half, hence half-life. So what that means is the growth factor, or I'm sorry, the decay factor for these will always be 0.5. No calculation necessary. You always know that your decay factor will be 0.5. So the only other things that we need to pay attention to is the initial amount of the isotopes, how many there were in the sample. What kind of things where will you find samples? Dinosaur bones, one would be something my son would say. Stones, rocks, moon rocks, Mars rocks. If we can find these isotopes that break down, they're kind of like a fat atom that are unstable, and so they break down at a certain rate over time. But each one of these isotopes have a different rate that they break down. But we measure them at the same amount every half of their decay process. But each one takes a different amount of time. So that's where this whole half-life time comes from. So we do use t here instead of x. That's the time period that we're measuring it over. The half-life time is going to be unique to each isotope, and then your decay factor will always be 0.5, and then there's your initial value. It's actually not a difficult problem. As long as you understand what each piece is. You understand that there's a time and a half-life time. You need to make that distinction. That's usually a little bit of a scenario where people get confused. So let's read through this problem. We'll do one, and we'll identify all the parts. Again, in every homework question, make sure that you write down the base half-life formula and each part that is in there. So we're going to go and try to identify these. So it says the half-life of a radioactive substance is the length of the time it takes for 1/2 of the substance to decay into another substance. That's what we've been talking about. To treat some forms of cancer, doctors use radioactive iodine. So here's a different application of isotopes. Okay, the half-life of iodine 131, and that's just a particular isotope. Don't worry about the number. It's not there to deceive you. It's actually its name, iodine 131. It means how many neutrons, extra neutrons are in its center, in its nucleus. It's got an 8-day half-life time. Okay, so what we're going to do is we're going to identify our half-life time. This is our H, and we're going to write 8, because that's the half-life time. So a patient receives 12 millicuries, and again, nothing numbered there. That's just a measurement, not one that you're probably familiar with, but it's a measurement they use for medicine, especially with these iodine isotopes. Okay, so they receive 12 millicuries. Well, you can kind of already see that that's the initial amount that they're getting. So they get an injection, a shot, and they get 12 millicuries, whatever this happens to be. It sounds like a small amount to me. That's going to be the initial amount that they receive. So we're going to identify that as our A value. Okay, and then it says how much iodine 131 is left after 16 days. So this is the time frame of measurement. So how many half-lives, how many times is it decayed by half, or our time? So that'll be your 16. It'll be straightforward like this. They'll word them like this, and all you have to do is identify them. And there's only 3 pieces, so you should do pretty good with that. So starting with our base here, we're going to try to figure this out. We'll put in our values, so we're going to find the 12 there. This will always be 0.5 for your decay factor. Never worry about changing that. Okay, our time frame is 16 days, but the half-life time, and that's a really bad exponent, but it is an exponent, 16/12. You'd put that into your calculator, and you would get kicked out. There actually comes out to be the number 3. And so if we put this in context, because all word problems we do need to write out, it says after 16 days there will be 3 isotopes of iodine 131 left in the patient. And that's a good thing. The more radioactive isotopes you have in your body giving off radiation essentially kills your cells. So you really don't want a lot in there. You want that to have a fairly fast half-life. Just to give you an example, the stuff we use to measure moon rocks or lava flows or dinosaur bones has hundreds of thousands of years of half-life, or even billions of years of half-life. Okay, so let's review real quick. You do need to memorize I do not believe I'm going to give this to you for the quiz, and they won't give it to you in any SAT or MAT or MME type test that you're going to take, so you do need to memorize these. So the first one here is your parent exponential model. It's about as basic as you can get: an initial amount, a growth factor, and some number of time or changes that happen in that time frame. Okay, a to the times b raised to the x. Then if we get a little bit more specific, if we have a rate that we're decreasing, it's not doubling. Doubling, you would use this one for tripling, things like that. If it's not something that's doubling or tripling, and you have some type of a rate or like 6.5% increase, like some of the problems we've seen, you would use the rate form of the exponential function or exponential growth function, where you have 100% of the original and that rate that's changing. Okay, because this one we can identify what doubling is, it's 2. We can identify what tripling is, it's 3. This one we have to add it to the original, so 1.065 for that particular example we're showing there. If there's compound interest, remember we get the compounding part. So we get it less often, or we get it more often, but we get less of it. And that's really the only addition between these two, is that you have to divide up your rate into the number of times that you're getting it and multiply it because you're getting it more frequently. And that's a compound interest one. And then we've got exponential decay, which is where we're actually decreasing, so our growth factor should be a decimal, right? And we have to subtract our rate from our original 100%. Usually, in most cases, these are larger decimals because usually decay isn't a giant thing. But I might be wrong. In the examples we'll see, they should be pretty big. They should not be, right, something very small. Rarely, in our examples at least, should they be really small decimals. So that maybe is a little clue to pay attention to when you're going over these. Hey, I might have made a mistake here. Miss Hallam said double check it if it wasn't a large decimal on those. And then half-life, super easy to write down and memorize because that growth factor is a 0.5. It is a decay, and the only thing that you have to pay attention to is the new half-life time, which is specific to each isotope. Okay, so there's your review. You have some homework questions in class. I'll see you for that when you get there. And, well,